my screen is visible, can you confirm in the chat box? Okay, thank you. Okay, I think we can start. Actually, the number of people registered for the course, it's very large number. So I was expecting a few more people, but I think people can join in between. Okay. Okay. So whoever has joined now, I hope I am audible to everyone. Okay, so people are joining. So let's wait for 2-3 minutes because people are joining. Okay. 7, 8. Okay, so let me start the session. So, hello everyone, welcome to the live session for the course Sensors and Actuators. Before starting the session, I'm telling you that I'm recording the session. Just giving you, so I'm just notifying you this. And this is week 1 of the live session. Let me introduce myself first. So I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. So right now, I'm not working on sensors. I did worked earlier on sensors. Mainly, I'm working on different devices, mainly fabrication of devices. So one big part of this course is the fabrication of the sensors. So I will be your TA for the live sessions, and I'll try to help you with the content of this course, and mainly in the fabrication part. If you have any doubt, you can ask me in the between. The idea of these live sessions are that maybe you have attended, you have done any other NPTEL courses also. So in many of these NPTEL courses, you have these live sessions. So the main idea of this live session is to solve problems, to discuss problems with you. So throughout the week, you learn the content of the course, and then at the end, maybe like typically on weekends or Monday or Tuesday, we'll have these live sessions. So I have done NPTEL live sessions earlier for different courses. This is for the first time I am doing this for this course, Sensors and Actuators. So this is new for me as well. And the number of people registered in this course is huge. So I'm expecting more number of people in the coming sessions, and I hope that the sessions will be useful for you. If you have any doubt, you can ask me in between. You can unmute yourself. I have given you the access, and you can write in the chat box also. What I will do in this courses is that first I will give you a brief overview of the content, so that everyone is in the same page. Ideally, you should watch all the videos before this live session. So I will not discuss much of the theory part. Mainly, I will concentrate on the questions. The questions will be similar to the ones given in the assignments, but obviously the questions will be not exactly same. Okay. And I will not discuss the questions, those are in the assignments, because the due date will be after the live session, so I'll not discuss those, but we'll discuss similar problems, similar questions. So if you have any doubt, you can ask. But since this is the first time I'm doing this course also, so don't expect that I can answer everything. I will definitely note it down, and we will have those questions, your doubts again, maybe in the next class, or I will have a doubt clearing session or like a summary session at the end if necessary. Okay. So do so I hope everything is clear and you know the format of this live session. uh, is there any question, or should I proceed? Okay. So if there is no question, I will start the content of this week. I hope that everyone has watched the videos. Okay. So this course is sensors and actuators. So first let me give you an idea about the topics those were covered in this week. So first we learned a few definitions and other things like what are need why we need a sensor and how to choose a sensor, and what are the basic working mechanism behind different sensors. Those things, a brief overview was given. So what is a sensor? So sensor, it is a device that can measure some physical parameter. Okay, let me write it here. So this physical parameter can be anything. One example is like say temperature. Okay, temperature sensors are used in many different applications in industries for safety purpose and to make different instruments also. Temperature sensors are integrated in many areas. So one example is temperature sensor. Okay, temperature is a physical parameter. A sensor that can measure temperature is a temperature sensor. Okay, and another part is for this course is actuators. So what is an actuator? So actuators are responsible for some physical movement of our device, right? So why we talk about sensors and actuators together? So you don't normally use sensors alone. So we often use sensors, and we often use sensors to make a system out of it. So you want to use a sensor to make simplify your life, or you want a sensor so that based on the sensor output you will do something, right? So often we make a system out of sensors and actuators. So a basic block diagram is it was not discussed in the class, but it's very basic, like how we use sensors and actuators together. So we have sensor, it will have some it will sense some physical parameter, and we will feed the output of the sensor to some decision making unit. Decision making unit can be a microcontroller, if you are from electrical engineering background and electronics engineering background, then you might have done this kind of decision making circuit using Arduino board or any other microcontroller. Okay, so this is a typical block diagram of sensors and actuators. So you feed the sensor output to a decision making unit, and based on the output uh, it will make some decision, and then it will give it to the actuators. Okay, so one example can be a very simple circuit you can make using Arduino board as a decision making unit. Say a photoresistor, uh, which is a sensor, and an actuator can be a relay which is connected to some light. Say a photoresistor, it senses light basically. So if the light is low, say the decision making unit or the microcontroller will give an output signal basically to light up a bulb, say. So this is like a basic block diagram of a sensor and actuator unit. Okay, so we will discuss about different sensors and actuators in this course. Now, many of the sensors that we will be discussing in this course will be of micro or nano sensors. So, what does micro and nano means? So, the characteristics dimension in this sensors will be in micrometer or nanometer range. So, micrometer is 10 to the power minus 6 meter, and nanometer is 10 to the power minus 9 meter. Okay, so this is very small dimensions, and we will discuss about their fabrication. So why we go for these small dimensions, the small sensors? There are certain advantages. One advantage, you can just directly say that the sensors are small. So suppose you want to use it for some biomedical application, then the sample size you need will be also less, right? And in many cases we have limited access of the sample, right? So the based on the design, the sensors can be very accurate, very precise, and very sensitive. So that obviously based on the design, but it simplifies many of the things, right? Especially in case of biomedical and biosensing application where you have very limited sample size. Now, as I mentioned, that the design of the sensor is very important so that it can accurately detect or accurately sense what you want to sense, and it should not sense what you do not want to sense. What I mean by that, the selectivity of the sensors should be very high. So for that you should go for a very specific design. You have to optimize the design so that it give you the desired response. Now suppose you prepared a design, right? Then you have to go for fabrication. Now because these are in micro and nano dimensions, so the fabrication of the sensors will also be challenging. We have the technology now that we can make micro and nano sensors, so that is not a problem, but it involves like a lot of sophisticated machines and other technology, like you may photolithography is one technique that was discussed in the class. So and different physical vapor deposition techniques and chemical vapor deposition techniques, those come into the picture of fabrication of micro and nano sensors. So we will discuss about the fabrication of the sensors in this course as well. Okay, so next part was how we choose a sensor. Now it depends on the requirement and application. Now I will give you an example. Say again, I will take an example of a temperature sensor. If there is background noise, I'm so sorry for that. I hope you can hear my voice rather than the background noise. Suppose you want a temperature sensor. Now, how you choose the temperature sensor, that depends on your requirement and where you are going to use it. Say you need a temperature sensor. There are many of the sensors available in the market, but say your requirement is you want to sense temperature which is close to 1000 degrees Celsius. Now you know that not many material will sustain at this temperature. Say if it is a flexible polymer, it will melt. Some metals will also melt, right? It will not sustain 1000 degree Celsius. So you need a material, you need a sensor with some material that can sustain 1000 degrees Celsius. So that depends on where you are going to use it, right? Now suppose you want to use it for some industrial safety application, say where if the temperature range is above say 990 degrees Celsius, you want some kind of like indication, say a red light will on. Okay. Now, in this case, maybe you will not care much about the accuracy of the sensor. So, even if the so the actual temperature is at 1000 degrees Celsius, but but the sensor will read it as 1010 degrees Celsius, or sometimes 995 degrees Celsius. Even if there is a variation in the actual reading with the actual temperature, but say you don't care about this variation. Okay, basically you don't care much about the accuracy of the sensor. Obviously it should be accurate, so the accuracy should not be like greater than plus minus 10 degree, because you want your sensor to give you an indication if the temperature is 990 degrees Celsius. So the accuracy should not be that bad, but you don't need a very accurate sensor. So in that case you can compromise with the accuracy, but you will need a sensor that can sense up to say 1000, or at least the range should be above 1000 degrees Celsius, right? Now, in many cases, say you don't want to sense the temperature to that high temperature, say you want to sense 100 degrees Celsius, but you want to measure it very accurately. So, 100, if the actual temperature is 100, it should show say 99.5 to say 105, in between this range. You don't want to go below 99.5, you don't want your sensor to read above 100.5, right? So you want a very accurate sensor. So for some specific application, then you don't need this type of sensor where the temperature range is very high. You don't need that type of sensor, but your accuracy should be high. So how you choose a sensor, that depends on your requirement and application, where you are going to use it, in which place. The environmental conditions also matter, because based on the temperature and environmental temperature and the relative humidity of the place and every other things, the sensor may behave in a different way. Okay, so you have to consider these factors. And if you are designing a sensor, then also you have to consider these factors, right? So in many times when you design a sensor, people who work on sensor, they test their sensors in different environment. Say what is the output variation with temperature, what is the output variation with relative humidity. So these analyses are important when you design a sensor. Okay, you don't want your sensor output to vary like based on place or at. So you don't want a sensor, you don't want to make a sensor that will behave differently in one day, or and it will show different reading at other day, right? Okay, now many of the sensors will be electrical in nature. Why electrical in nature? Can anybody tell? I hope there are people in the meeting, so uh, just this is a very general question. What is your point of view that why many sensors are electrical in nature? can write in the chat box. You don't have to leave the meeting. Okay. What is the pattern of exam? So that will be notified to you. So I will mainly do the live sessions. So if you have any other question, then you can discuss in forum, and the exam pattern, I think that will be discussed later. Yeah. How to confirm we select the right sensor in terms of selectivity, any parameter that can confirm selectivity of a sensor. So as I mentioned, you have to consider several things, like not only sensitivity or selectivity. uh, of course you want a sensor that is selective enough so that it sense a particular, say for example gas sensor. If you are designing a sensor for say ethanol sensing, it should sense only ethanol, right, not other any other gas. So it should be selective, but selectivity is not the only parameter while selecting a sensor. There are several other terms like repeatability, reproducibility. What is the range of the sensor? Say if it can sense ethanol, but what is the resolution? What is the minimum amount of ethanol it can sense? Okay, and what is the range? Say it can sense from 10 ppm to 1000 ppm, so that will be the range. So basically it depends on your application. And if in an environment where you are using any other gas will not present, like except from the gases available in like normal and atmosphere, then probably you will not care much about the selectivity also. Basically what I want to say that it depends on your application and where you are using. Any parameter that confirm the selectivity of the sensor. So selectivity of the sensor, uh, if you are working on sensors, like you are designing a sensor, then you have to see sensors are of different type, right? uh, it depends on your sensor, what is the basic mechanism, the working mechanism behind your sensor. So there is no like general parameter that can confirm the selectivity of the sensor. So if it is like a chemical reaction based sensor, then I think that it will be very specific, because certain chemicals will react with certain chemical, right? But then again it depends on your sensor design. Okay, if it is like a chemicals, most of the time the sensors which are based on some chemical reaction, those are very sensitive, because uh, you can do that, you can write the chemical equation, you know that this will react with this, and this amount of chemical A reacts with this amount of chemical B, then it will give the byproduct will be chemical C of this concentration, so that you can measure. Because we used material and materials have their own resistivity. So this is for the solution, for the question that I asked, why most sensors are electrical in nature. Yes, you are correct in a way, because many of the sensors are resistive type, that I agree. But the main reason why uh, we use electrical sensors mostly, as I mentioned, that ultimately we want to do some work with the sensor output, right? You are sensing something, you are sensing for some purpose. You are sensing light, the example I have given. What you want to do, if the light is low, you want to light up a bulb, right? So it is very easy to make a system out of an electrical signal. It is easy to make a system from say a sensor that gives electrical output. So electrical output can be voltage and current, You can directly give it to some microcontroller. You can do some work. You can fit that output to a relay, fit that output to run a motor. uh, Motors can be of different type also. You can make a very circuit easily of that. So that is why most sensors are electrical in nature. Okay, so we can have an analog output, say in terms of voltage, from 0 to 5 volt. I will write it here. So suppose you have an electrical sensor. The output is an analog signal, which is a voltage signal. Say it is in the range 0 to 5 volt. Say, then what you can do, you can use a ADC, analog to digital converter. Okay, and you can say use a 10-bit ADC. Okay, so that will give you output from 0 to 1023 in this range if I convert it to decimal. And then you can write a code very easily in a microcontroller that from 0, if the output is between 0 to 255, do some work 1, and if it is between 256 to say 512, do some other work. Okay, you can decide it. So you can very easily make a system out of a sensor. That is why many sensors are electrical in nature. And you know that there are direct sensors and indirect sensors. And in direct sensors you get the electrical signal as an output directly. If it is an indirect sensor, we often convert the the output signal, which is a non-electrical signal, to some electrical signal using some conversion mechanism, and we use it in our system. Okay, okay, let's go to the next slide. Now, a few other topics those were discussed in the week. One is the substrates. Those are used for sensor. So we mostly use silicon, especially in micro and nano sensor fabrication. We use silicon, but other substrates are also used. Say glass, PDMS. If you want to make a flexible sensor, again it depends on your sensor design and application. So how silicon wafers are fabricated, that was discussed in the class. I have given you this diagram. So this is how silicon wafers are made from a melt of SiO2. Basically the SiO2 is purified, and then molten silicon, from molten silicon, silicon wafers are made. You can, if you are interested, then you can read about this process. It was discussed in the class also. I'll not go into the details. Then there are different types of silicon wafers. So 111 p type, 111 n type, and I hope that you are already familiar with different types of silicon wafers. Okay, so these are this on substrate. Those are used in designing sensors, in fabrication of sensor. Why we mostly use silicon? Because we are talking about micro and nano sensors. We are talking about photolithography and other deposition techniques to fabricate these sensors, and this technology, uh, this photolithography and other technologies are well developed in silicon. So we often talk about we often want to make a sensor for which the technology is already available, and for silicon everything is well known. We know that we can easily grow silicon dioxide, and we can make an insulating layer on top of silicon. We can make SiO2 very easily. We already know many of the properties, what chemicals react with, what are the chemicals that can be used in case of photolithography of silicon. Okay, so all these things are well known, well developed. That is why we mostly use silicon, but not necessarily. Say if you want a transparent sensor, then you will go for a transparent substrate. say glass or PDMS if you want a flexible sensor. Okay. Next, a significant portion of this course, at least in week 1, that was discussed was on micro heaters. So this is a one kind of design, one design of a micro heater. The design can vary, depends on you, depends on application. So this is like a series resistance. So the formula for resistance is R equal to rho L by A. So this was discussed, and based on the material, based on the size, and how how we are making the design, the resistance of the micro heater can vary. Now what a micro heater will do, we will apply an electrical signal in this heater, and the electrical signal will be converted into heat due to Joule heating, and how much heat will be generated, that depends on the length of this material, the physical dimensions of this heater, as well as the material that is being used in heaters. So micro heaters will be used to make many like in along with many sensors. Say if you are familiar with gas sensors, and many gas sensors are of MOS type. So this MOS is metal oxide semiconductor, say ZNO or SNO2, these materials. And many of the time this sensors works at elevated temperature. We need to provide certain amount of heat so that the sensor will work. So many times micro heaters are integrated with the sensor design. So the designing of a sensor part along with the micro heater, that also comes into the picture while designing the whole sensor. Okay. Next, the fabrication techniques were discussed. What is PVD? So PVD is physical vapor deposition. Okay, so why we use PVD or CVD, chemical vapor deposition, all these techniques we basically use to make a thin film of material. Okay, so you have a substrate, you want to deposit your material, so this material will change its resistivity based on some physical parameter. Okay, and you will measure the resistance, you will convert it to equivalent voltage, and that's how you will make your sensor. So this material it has certain resistivity. So how we will deposit this material, using this kind of technique, either PVD or CVD technique. Okay, now say after deposition you want to make a pattern of it. Say, so in many times what you do, we have a material and we want to make an electrode here. This electrode can be the design of this electrode can vary. You can have an interdigited electrode or any other design, but say you have an electrode, this is your material, sensing material, and you will measure your resistance here. Okay, now to make these electrodes here, what you will do, because you want a thin line of these metals, okay, you will do a photolithography. So we will discuss about photolithography maybe in coming weeks. Okay, so photolithography is a patterning technique, and PVD and CVD, these are deposition techniques. Okay. And next part of this week's content is in the course, different microfluidic sensors were discussed. Okay, some examples were given. I will not discuss those again. I hope that you have watched the videos. If not, you can watch those again. Okay, what one thing I want to say, that this course, specifically the sensor, the topic is so this is a multidisciplinary subject. Okay, you have to remember this. Now you should know that not everyone is like an expert in everything. So in many of the examples given in the course, those are on biological sensors. So sometimes maybe I will not be able to explain you everything because I'm not working in this area. I'm also learning along with the course. But the basic idea, like the basic approach, if you want to design a sensor, those will be similar. So it is a multidisciplinary subject. If you are working in say biological sensors, biomedical applications, or in chemical sensors, so you should know about biology, chemistry, electrical engineering as well, because ultimately most of the sensors are electrical in nature. You should have knowledge about fabrication, because ultimately after designing you want to fabricate it, right? So it is a multidisciplinary subject. There will be different topics which may not be familiar to me, may not be familiar to you, but we will learn in this course together. Okay. Now, microfluidic sensors, these are mainly used in biomedical application. Now, there are several advantages of using microfluidic sensors. You know that in microfluidic sensors, the channel dimensions are in micrometer. So the characteristic dimension is in micrometer range. Okay. So the advantage is that if you use a microfluidic sensor for biomedical sensing, then as I mentioned earlier, it does not require a lot of sample. Okay. And this is a very important advantage, because many times in case of biomedical or biological experiments, you will not get a very large sample size. Okay. So these sensors can provide a very precise result even with a very small amount of sample. Okay. Now the examples tools were discussed. One example was to test the efficiency of a drug. Okay. Or a set of available drugs. Okay, I hope you remember this example. Okay. So again, if you remember the example that was discussed in the class, here you can notice that you need the knowledge of biology, you need the knowledge of electrical engineering, because the sensor that was discussed is an impedance based sensor. The physical working mechanism behind the sensor is the impedance change. Okay. And then to make the sensor, the fabrication of the sensor part, so you should have the knowledge of fabrication as well. Okay. Then there was another example that was discussed, that is to study the efficiency of a drug for a particular on a particular person. Okay. So basically person specific study can be done using microfluidic sensor. So basically these are used in biomedical sensing to mimic living organs. Okay. So this is very important, because ultimately you want to test your medicine, your test your device on uh, on a person, but you cannot do it, like you cannot test the drug directly on a person. So you can mimic the organism, the particular problem you are targeting. uh, you can make a system using a microfluidic sensor and you can test there. And in earlier days, like people used to test this on animals, if you can remember. So but which is, it's not very good, right? You don't want to test your drugs on animals and other living things. So in this way, microfluidic sensors are very useful because you don't have to do that. You can mimic this cells, mimic this system in a test tube or in a lab setup. Okay, so I guess this is briefly on the topics those were discussed in the course. Do you have any doubt? I will wait for a couple of minutes and then I will go to the questions. In modeling, how do you define the selectivity of a sensor? Say, uh, I, if I have understand your question correctly, say for example, you are designing a sensor which is of resistive type. Based on the physical parameter, based on the concentration of the physical parameter, the resistance will change, resistance of your material, sensing material. Now, the selectivity will be, say,
Yes.
okay, it will be better if you mute. Okay, so uh, say your resistivity, the change in resistivity is it should be highest for the material that you want to detect, right? Let me do this. Okay, let's. Okay, so back to your question. Say you are measuring the change in resistivity, and you want your selectivity to be highest for material A. Say, now you will compare the change in resistance due to material A with say B, C or D. Now how much change in resistance is acceptable, that depends on you, like that depends on your design. Say the change in resistivity, the minimum change in resistivity you can detect with your system. Obviously you are measuring a change in resistivity with some system, right? Say with a multimeter, then it can measure say 1 ohm. If the change in resistivity due to chemical B, material B, C or D is less than 1 ohm, will you care? So you won't care, right? Again, it so this in modeling, if I have understood your question correctly, then the selectivity will be what is your output, sensor output, right? If your sensor output is change in resistivity, then how much change in resistivity you can accept, you can afford, uh, like if it is a different material uh, than the material that you want to sense. Okay, I hope I answered your question. How can we decide the correct orientation of silicon substrate? So you can see the diagram here. So this is convention, right? This you can see the straight line, this is the primary flat, and this smaller straight line is the secondary flat. So in here if you see 100 n type, this is the primary flat and this is the secondary flat. These are opposite to each other. Okay, uh, and this is n type, so this is the convention. And in case of p type, so the primary flat is here, the secondary flat is here. So this is for 100, and in case of 111 for n type, This is the primary flat, this is the secondary flat, and this is the primary and secondary flat basically at the same angle in case of 111 p type. Now what type of silicon wafer can be used for gas sensing application, I'm not sure, but one thing I can tell you that, see, 100 and 111, those orientations will have uh, different number of atoms. Like, have you seen the crystal structure of silicon? So it is FCC lattice. Basically, it has diamond structure, right? Two FCC lattice interpenetrated, uh, which is translated by 1/4 of diagonal. You can see the crystal structure of lattice. Now, silicon atom. Now, if it is a 111 crystal orientation, uh, the atoms at the surface, number of atoms will be different than 100. I hope you are getting my point. You will understand this if you look at the crystal structure of silicon. Okay. Now, if you need more number of atoms uh, of silicon, so it will have dangling bonds at the surface, right? Silicon will have some dangling bonds, or not each of the silicon atoms will be directly connected with other silicon atoms. So 111 orientation will have like a different kind of dangling bond, not different kind, maybe number of dangling bonds will be more, that is what I am guessing. Okay. And 100 will be different, but I don't think you will directly make your sensor on silicon, because there will always be a thin layer of SiO2 on silicon also. So whether this will impact your result in sensing, that I am not sure. Okay. Because if there is an SiO2 layer in between, then it should not affect much. Okay. If there is no SiO2 layer and you are using it directly, then the dangling bonds of 111 orientation and 100 orientation will play into role. Okay. You can just look at the crystal structure. I will go into the questions part, because uh, many of the students may have joined because of the questions, for the questions. Okay. So I'll write down the question, and you can tell me the answer in the chat box. Which of the following are categorized as physical vapor deposition technique? Option A is thermal evaporation. B is sputtering. C is thermal oxidation. Option D is both A and B. Option E is both A and C. So this is the question. Tell me the answer in the chat box. I will give you 1 or 2 minutes. What is a physical vapor deposition technique? It is a technique that is used to deposit uh, metal or dielectric films on top of the substrate. Option D. Yeah. Okay, option D is correct. Both thermal evaporation and sputtering are physical vapor deposition technique. Why not thermal oxidation? Thermal oxidation we use to grow oxide layer, not deposit oxide layer. So what deposition means? You have a target, okay, and you have a substrate, and you deposit material from target to the substrate. What we do in thermal oxidation, we say heat our substrate. In case of silicon, we heat it at high temperature, and the oxygen present in the environment that will react and will form SiO2. So this is growth, not deposition. Clear? Okay, option B, yes, sputtering is physical vapor deposition techniques as well as thermal evaporation. So the correct answer is D. So I will share these slides. So I will write few notes here also. So I will write down the definition of physical vapor deposition. The short form is PVD. CVD, chemical vapor deposition, is also deposition technique, but there some chemical reaction is involved in those processes. Okay. Oh, let me first write down the answers. These are vacuum deposition techniques. Why vacuum? Because you don't want material from uh, other things to react with the substrate. Okay, you want only the material from your target. Say you want to deposit aluminium on some substrate, then you want to only deposit aluminium, right? So you want your material from target. So what you do, you first create a vacuum in the system. Whether it is a thermal evaporator or sputtering, you create first vacuum and then you do the deposition so that no contamination happens. Okay. These are vacuum deposition methods used to deposit thin films. So mainly these films are very thin. You cannot grow very thick films. Maybe you can grow maybe in micrometer. Okay, otherwise it will be very time consuming. On different substrates, those substrates can be silicon, glass, quartz, sapphire, which is Al2O3. Now the substrates, sometimes it depends on what material you are depositing also. So certain material will not will make a very good film on certain substrates. That depends on the adhesion between your material and your substrates. Okay, so that's why we use different substrates. Also depends on the application as well. So what happens in PVD? There is target, okay, the material you want to deposit. Some part of the target will go to vapor phase and it will condense on top of a substrate. So physical vapor deposition, in physical vapor deposition techniques, no chemistry is involved. Mainly you use physical force to remove material from target and then to deposit on the substrate, right? So the first physical vapor deposition technique, so this is sputtering. So this is a diagram of a sputtering system. So this is the sputtering chamber. First we create vacuum so that there is no impurity in the chamber. So you can see this is the sputtering target. This picture is not very clear. So this is sputtering target and this is the substrate. So basically what if you have not seen a sputtering system, so there will be a holder. You'll place your substrates here. So in the system we have, in our lab we paste our substrate at the holder, and then first you create vacuum and then you introduce sputtering gas from some inlet here, say. Now you will apply an electrical signal between the substrate and the target. It can be DC, it can be RF as well. Okay, that depends on your sputtering target also. In case of metal we can use DC. In case of dielectrics we typically use RF signal. And then the sputtering gas, which is typically argon, that will become like argon plus an electron. So basically there will be a creation of plasma in this region between substrate and the target. And when this argon plus ions will hit the target, it will eject um, from material atoms from the target, and these atoms will sit at the substrates here. Okay, it will eventually cover the whole substrate and will get a uniform thin film. Okay, so this is sputtering. So it involves ejection of material. I hope you can understand my handwriting. Okay, now typically argon gas is used, so we need a gas which will not react with our target or substrate, so we use the inert gas. And why we use argon, say we need a material, we need an atom uh, whose atomic weight is close to the material in the target. Okay, so that it hits the target and the material gets ejected. Okay, so uh, if we want to deposit a material which is of lighter weight, then neon is preferred. Okay, if it is a heavier material, heavier target material, then krypton or xenon is used. Mostly we use argon, like in most cases. I'm not sure for which what are the material for what are the targets for which xenon or neon is used. You can look if you are interested. Okay. Now another physical vapor deposition technique is evaporation. So you know what evaporation mean. Evaporation is like evaporating or creating a vapor phase of a material. Now you can create or you can evaporate a material by applying energy. You have to melt the material first. Okay, and this you can do by using by applying temperature, which is known as, the process is known as the thermal evaporation, or you can do it using by electron beam, which is known as the e-beam evaporation. So this picture is of thermal evaporation. Okay. So this bright thing you can see here, so this is a boat and these two are electrodes. Okay. So the electrodes, the boat is connected to this electrodes, and we apply a current, and that ultimately heat up this boat, and the material, target material, say aluminum, you want to evaporate, or say titanium or any other metal you want to evaporate, that you will place at the boat. So boat, it can have different shape, but it is something like this. You connect your electrodes here and you place your material here. And why this is bright? Because you are applying very high current, so it became bright, and the material will it will melt. Okay, and then it will evaporate, and first you create vacuum, so there is no other particle. Okay, this evaporated atoms will be directly sit on the substrate, so which will be placed, say, here. Okay. And now in this case vacuum is very important, so that the evaporated atoms does not get scattered. Okay, the atoms will directly uh, sit at the substrate. Okay. Now here one more thing is that you have this board and you place your material that you want to deposit on this board, right? So you want to apply very high temperature so that this material will melt, but you don't want to apply that much of heat so that the board will melt. Okay, so typically tungsten, molybdenum, all these materials are used to make this board. Those will have higher melting point compared to the material you want to evaporate. Okay, that is very important. So you cannot use a material to make a boat which will have lower melting point. Okay. So this is about sputtering and evaporation, or PVD, and we use regularly these methods to deposit a material in many sensors. So you can use a sensing film, or many times metal deposition using evaporation is used to make electrodes in sensors. Okay. Hope it is clear. Go to the next question. I will write down the question first. Okay. For a sensor, which of the below signal can be used to have a readable format in the sensor output? Option A is optical, mechanical, C is electrical signal, D is All of the above. What is the answer? You can tell me in the chat box. I will wait for couple of minutes here. Do I have an answer? Option D, option C, option D. Okay. I think there are more people in this meeting. Option A. So why this question is that readable format in sensor output. So see the physical parameters a sensor senses, say temperature. We want the output of a sensor is in some readable format. Okay. Otherwise, it will not be useful, right? Uh, we we make a temperature sensor. It should display the temperature. Like we don't know what mechanism behind it, but it should display us something, or we should have some indication, right? That is why this question is that what kind of signal can be used as a readable format. Of course you want you can have a display to display the number, but there can be other type of signals also which a sensor can have. Okay, so that is the question. I think many people have answered as option A, D, or okay. So let's see one by one. For a sensor, which of the below signal can be used to have a readable format in the sensor output? Okay, first option is optical. Use a different color. can we have a optical signal as an output of a sensor? Yes. How? So I will give you an example of an sensor that uh, that can be so it's a real life example. I don't know if you have heard about LFIA, lateral flow immunoassay. So these are one type of sensor mainly used to sense again uh, in biological sense something like biological sample. Okay, so if you remember during COVID there is this rapid antigen test. Okay, you put your sample, you put your like sample somewhere here, and then there is this like display window where, say, I don't remember how it worked actually. So say if it is one red line then it's a negative, it's a two red line then it's a positive, something like that. Now this indication, these lines that you see like visually through your eyes, so these are optical signal. Okay, so these red lines, so this red color, these are basically gold nanoparticles. If you know about nanoparticles, then gold nanoparticles are red in color of certain size. So these are often used in biomedical sensing or biological sensing because just by looking through your eyes, you don't have to use a sophisticated instrument. You get an qualitative idea about what is happening. So here you don't know what, in case of like some disease detection using LFI, you don't know like how serious the disease is, but at least you can say that okay, but this test is positive or negative. Okay, so this is like an optical signal. Or as a sensor output, you can have the output as an LED. Okay, but again that will be also an optical signal. Okay, so we can have the output of a signal, uh, output of a sensor as an optical signal. To convert the sensor output in a readable format, we can describe the output of the sensor through a optical signal. Okay. Then the second option was mechanical signal. Can we have a mechanical signal as the output of a sensor which is of readable format? The answer is yes. Again, I will give you one example. Say pendulum. Okay. Say you have a sensor. The output of the sensor is that there is a pendulum and it moves back and forth with certain frequency. Now say if the sensor output is normal, by normal I mean there is you are there is no activity, it's in the stable state, it will not move back and forth, say it will be in a stable position. Now due to some activity, say you have the output in form of a mechanical signal, the pendulum will move. Okay, now this will indicate that something has happened, as well as you can calibrate in such a way that the frequency of this oscillation or the amplitude of this oscillation will give you an idea about what is happening, what is the input to the sensor. Okay, this is one example. We can have other type of mechanical signal as an output also. Okay, next is electrical signal. Obviously we can have, in fact we mainly have electrical signal as an output of a sensor. Okay. Why we use mostly electrical signal? As I mentioned earlier, electrical signals are very easy to process. By processing I mean we can use the electrical signal, we can process this, we can do certain signal processing, and we can convert it to from analog signal to digital signal, or digital signal to analog signal. We can amplify it very easily, even if it is a very low amplitude signal or a low value. we can easily amplify it, we can reduce noise with our signal processing tools. So it is very easy for processing. So processing of sensor output is also important when there are so many sensors are integrated, especially in case of say uh, in an IoT system, okay, Internet of Things, okay. So electrical signals are in that way very easy to process, and we try to design our sensor in a way that it gives us an electrical signal as an output. But it is not necessary that we will always design a sensor that has an electrical signal as an output. We can have optical, mechanical, or any other type of signal as an output, which will be uh, like easy to read, which will be in readable format, okay. So the correct answer will be D, okay, all of the above. Can you think of any other type of signal that can be used as an output of a sensor? And is there any doubt in this question? You can think of any other type of sensor output, okay. If there is no doubt, let's go to the next question. Let me write down it first. Which of the following can be measured using a piezoelectric transducer? Is velocity, displacement, force, sound. So what is the answer? Which of the following can be measured using a piezoelectric transducer? Velocity, displacement, force, or sound? And it by what can be measured, I mean what it can primarily measure, not the secondary effect I'm asking, okay. You can tell me the answer in the chat box. I will wait for a couple of minutes again, and I will explain how piezoelectric transducer works, what is the mechanism behind it. Option B, C. B is displacement, C is force. So what I have mentioned is that what can be measured using piezoelectric transducer, what is the primary quantity it can measure. That is the meaning of this question, not the secondary effect. Okay. Option C. Okay. So option C is the correct answer. Okay. um, I will write down. I'll note down few things also for your reference. I'm making this slide. So what a piezoelectric transducer do? A piezoelectric transducer is a device that converts mechanical energy is, say, pressure, force, kind of similar, okay, into electrical energy. Now, due to pressure and force, also it may the thing may attain some velocity or displacement, or due to sound, also there can be some pressure or force. But those are the secondary thing. The primary thing is that in piezoelectric transducer, mechanical energy, which is pressure and force, is converted into electrical energy, and vice versa. Why vice versa? So this is a piezoelectric transducer that is was mentioned in the question, right? It's not a piezoelectric sensor. So sensors are normally unidirectional. It converts, like it sends some physical quantity, converts it to some other format, in readable format, right? Say electrical signal or optical signal. uh, in case of transducer, it converts one type of energy to another type of energy. You know the definition of a transducer, and transducers are mostly bidirectional. That means this, vice versa. uh, if it is a transducer, remember that this converts one form of energy to another form, and these are bidirectional devices most of the time. Whereas sensors can sense some physical quantity into electrical signal most of the time, or to some other readable signal format. These are not bidirectional. Okay. And piezoelectric transducer or sensor is works using that uses piezoelectric effect. Okay. Certain materials show this kind of piezoelectric effect, where when you apply a force to the material, then an electrical signals generates. So example of this kind of material is quartz. Okay, one example that I just looked into the internet. You can find other example also. I'm not very familiar with this kind of piezoelectric crystals, but you will find there are examples using which you can design a piezoelectric sensor or a transducer. Now, what is this piezoelectric effect? So, what happens in this kind of material where it shows piezoelectric effect? So, uh, so the materials will have something crystal structure, right? So, this is some material which is a piezoelectric material. It is in the normal state, okay. It has electrons and protons and everything, so it is electrically neutral, and charge distribution is just such that there is no net electric field is present, so it's a bulk crystal. Now when you apply pressure or force, what happens here is that the crystal structure in this material changes, okay. The crystal structure deforms. i'll just I'm just writing it, you will understand. So crystal structure deforms, because of which the charge distribution changes, okay, and that will result charge separation. So there will be positive charge at one side of the crystal and negative side in another side, another part of the material, okay. So this will generate electric field. That's how electric field or a voltage is generated in case of piezoelectric material, and that can be useful to sense pressure or force, this kind of mechanical energy. Okay, if you want to design a force sensor or pressure sensor, then you can look for this kind of material that shows piezoelectric behavior or piezoresist behavior. Okay. Okay, then I have this question. So this I have kind of discussed earlier. Okay, when selecting a sensor for specific application, what factors should we consider? So there are option A, B, C, D. A is environmental conditions, sensor specification, and economic factors. B is sensor size, durability, and power consumption. C is installation cost, maintenance cost, and manufacturer reputation. D is economic factors, sensor availability, and calibration requirement. So, how to choose a sensor, that was discussed in the one of the class also. So, I hope that you can answer this question, and I want to give you reasoning also in few lines. Don't just We don't have to write a big paragraph in the chat box, but you can just uh, tell me why you are choosing a particular option. So, okay. I'll wait for 2-3 minutes so that you can write. Yeah. Yes, option A. Can tell me few reasons also. answer? Option, so few of you are saying it is option B and few are saying option A. Okay. Okay, see, it was discussed in the class. While selecting a sensor, we have to consider three things. Okay, I will give you the answer. First is the environmental condition, second is the economic factors, and third is the sensor specification or characteristics. So the correct answer is A. Now, why? So it's not that these are incorrect, but environmental conditions, sensor specification, and economic factors basically covers everything. Okay, let's see one by one. So first is environmental condition, right? Now it will depend on which environment you are going to use your sensor. Again, if it is for a specific application, say you want to there is some high temperature process going on in an industry and you want to measure that temperature, the example I gave you earlier, right? You want to sense very high temperature, so you will obviously go for a sensor that can sense higher temperature range. Okay, if you want to sense 1000 degrees celsius, the sensor, the maximum range of the sensor should be above 1000 degrees celsius. This is very application specific. Again, say you want to use a gas sensor, you will look in which environment you are going to use the sensor. You are using the gas sensor in some industry that releases a very toxic gas, like carbon monoxide or something, hydrogen, some other gas that can be flammable. So you want a very specific sensor to sense those gases, the concentration of those gases, so that it gives an indication that okay, the concentration of gas is too high, it is very risky. So you will use that specific gas sensor in that situation. You want to use it for say alcohol detection, the example that was given in the class, the drink and drive. So you will use that ethanol sensor. So environmental condition where you are going to use it, this is one of the primary factor while choosing a sensor. Next is I'll talk about first economic factor. Okay, you want your sensor to be of low cost, like we don't want to pay a very high amount for a sensor, especially when it comes to IoT, internet of things. In IoT systems, many sensors are used. So if the cost of a particular sensor, individual sensor, is very high, then the overall cost of the system will be very high. If you want to make your home smart and you want to use certain sensors, you will obviously go for the sensor which are of low cost without compromising the quality. Now what in case of sensor, what quality means? These are sensor specification or sensor characteristics. How you define a sensor, how you say that the sensor is good or bad in case of a particular application, for a particular application, you consider it by looking at certain numbers in the data sheet, certain values in the data sheet. So what are these? Say what is the accuracy of the sensor, what is the say resolution of the sensor, say if it is a gas sensor, what is the minimum concentration of the gas that it can detect. Then the selectivity, obviously we have already discussed in today's session what is selectivity, TVITY. Then you obviously want your you will also consider the range of the sensor, as I mentioned, in case of environmental condition where you are going to use the sensor, what is the typical environmental condition in for that application. Okay, what is the range of the sensor? Range means what is the input range it can sense. Okay, then what other terms can come? Say repeatability, then the reproducibility, linearity. I'm introducing some of this term. Many of the terms maybe you are already familiar with. If you work on sensor, then you already know what these means. Okay, so these are like the parameter using which we define a sensor. How good a sensor is, we and how bad a sensor is, we define using these parameters. What is the accuracy, resolution of the sensor, selectivity, range, repeatability, reproducibility, whether the sensor is linear or non-linear. We typically want a linear sensor because it is easy to again process a linear output. Okay, so these are terms you should be familiar with. You can if you are not aware of these terms and the definition of this term, you can search in Google or any other textbook that is related that is on sensor. Okay, so again everything is application specific, and I encourage you to look into the data sheets of different sensors, then you will get an idea about these terms. Okay, uh, try to look for a data sheet that has detailed information. Like in some data sheets they don't give all of the information. Try to find a detailed data sheet and look for these terms. Like if it is you can search for a gas sensor, you can see what is the selectivity. There will be some graphs, okay, that this sensor is selective to this, and the minimum resolution is that it cannot detect below this concentration, and the repeatability graphs will also be given, that we have already tested this sensor for this many number of times, so the lifetime is very high for the sensor or something. You will find everything of this in a data sheet. And if you are designing a sensor, then these are the things that you should keep in your mind. Okay, and here the other thing, sensor size, durability, power consumption, all of these things come in sensor specification. Installation cost, maintenance cost, this comes in economic factors. We want both of these to be low without compromising the quality and manufacturer reputation. Yes, we do care about manufacturer reputation because that means the sensors will be reliable, the reproducibility of the sensor will be good, repeatability will be good, right? And then economic factor, that we have already discussed. Sensor availability, okay, so we should have a sensor first. If we then we can only use. And then calibration requirement, I hope you know what is calibration, or I can briefly discuss at the end if time remains. Okay, so calibration is basically the relation between input and output. We do experiment and then we determine what is the relation between input and output. In some sensors you have to do the calibration again and again in some systems, and in case of certain, because this like sensors deviates with time. Okay, there are some material uh, that is used in the sensor with, say, uh, like repeated use, or due to environmental degradation the material is degrading with time, then you need to do the calibration more frequently. So these things comes into the picture. But overall, option A, these three things cover everything. Okay, and you have to consider everything while selecting a sensor. We hope it is clear. Okay, exposure to the vibration and other factors. Okay, yes, like environmental factors can affect sensor performance, so you have to like that is what I mentioned earlier also. Say many of the sensor behaves differently at different temperature and different relative humidity. You don't typically want that variation unless your sensor is not a temperature sensor. You don't want any variation due to temperature. Unless your sensor is not a humidity sensor, you don't want any variation in your output due to relative humidity. Okay, so again, this depends on the type of the sensor and for what application you are using. Sensor specification, yes, you can look into the definition of all of these terms. Okay, thank you for this explanation. I think it's a very good brief summary of the points that I have discussed. Okay, let's go to the next question. One topic was discussed briefly is a photodiode. Okay, this question is on that. Which of the following is true for photodiode? First option is the wavelength of light illuminated upon the photodiode must be greater than the cutoff wavelength. I hope you know what it means. If not, I will explain. There is no photo generated current. In forward bias. Three is the photodiode is used in reverse bias. Fourth statement is the reverse bias current is sufficiently larger than the photo generated current. Now the options are A is 1, 2 and 3. These are true as per this option. Okay. Option B is only 3. Option C is only 1. And option D is all of these statements. Okay. So what is the answer? Try to answer it if you are familiar with photodiode. It was discussed in the class. If you cannot answer, I will anyway give you the answer. Just check it once. Option A. So 1, 2 and 3, all of these are correct. So think about it again. I can say that option A is not correct. Option B. Okay. So I'll not wait any more time. I will go into the solution. Okay, let's see the statements one by one. Okay, first statement is the wavelength of light illuminated upon the photodiode must be greater than the cutoff wavelength. So first of all, I'm assuming that you already know how photodiode works. So first let's see statement 1. So what happens in photodiode when light is incident, then electron hole pairs are generated. So this is some material. I'm not drawing the photodiode or depletion layer, just a normal material, just consider it. And light is incident here. The energy of light is h nu. You know this is the energy of a photon. H is the Planck's constant, nu is frequency. I hope that you are familiar with energy of a photon. Okay. Now h nu electron hole pair will be generated and electrons will be it will create an electron hole pair if this energy, okay, is higher than, greater than or equal to band gap of the material. Okay, then only electron and hole pair will be generated. Okay, so the equation is h nu, a general equation is phi plus km. This is the kinetic energy of the material. So here phi, don't worry about the terms, I'm just giving you the equation so that you can understand. This is the work function in case of metal, but we are considering photodiode, so it will be easy. Okay, this is in case of metal. Now this is the this we can write it as some h omega c. This is the cutoff frequency, okay, which will be equal to h c by lambda c. So this is the cutoff wavelength. So h nu also frequency, we can write it as c by lambda. Okay, you know the relation between, so c is the wavelength This is the speed of light. You know that photon is basically light, so you know the relation with the velocity and frequency and wavelength, right? So nu is equal to c by lambda. This will be equal to hc by lambda c and plus km, so some kinetic energy. So here lambda is the wavelength of incident photon, and lambda c is the cutoff wavelength, right? To generate electron hole pair in case of semiconductor, this should be so this relation has to be followed. So hc by lambda should be greater than hc by lambda c. In case of metal, electrons will be ejected from the material if hc by lambda c is greater than hc by lambda c. Hc by lambda is greater than hc by lambda c. So this is cutoff wavelength. I'm just discussing a general case, not particularly in photodiode. Okay. Now you can see this is a inverse relation. So hc by lambda should be greater than hc by lambda c for electron hole pair generation. Okay, that means lambda should be less than or equal to lambda c. So the wavelength of photons should be less than the cutoff wavelength, or the energy of the photon should be more than the band gap of the semiconductor to create electron and hole pair. Okay, this is very intuitive. You have to provide more energy to create electron and hole pair. Basically, that's it. So this is an inverse relation. So the statement is the wavelength of light must be greater than the cutoff wavelength. So this is not true, right? We have just seen that lambda should be less than or equal to lambda c. Okay, so first statement is false. This is false. Let's go to the second statement. Second statement is there is no photo generated current in the forward bias. If it is a diode, forward bias will be if we apply positive voltage here, negative voltage here. Okay, the forward bias current IFB, I'm just writing, this is typically in the range of hundreds of microampere. Okay, this is in the range. Now if light is illuminated here, then there will be still some depletion region, there will be still generation of electron and hole pair, but the current due to this electron hole pair generation, that will be very small compared to the forward bias current. But it's not like that if the energy of the photon is sufficient, it's not like that the current will not be generated, electron and hole pair will not be generated, or there will be no current. The problem is that you will not be able to detect it if it's not that high, because forward bias current is already very high. So statement 2, okay, this statement 2 is no photo generated current in forward bias. That is also not true. There is current, but you cannot detect, okay, because it's very small. So this is also false. Then third statement is the photodiode is used in reverse bias in general. Again, that is true. That was discussed in the class also. Why we use mostly in reverse bias condition photodiode, we apply negative voltage here, positive voltage here, and light shines here, because reverse bias current is very small. Okay, we want it to be as less as possible. Okay, that's will be in nano ampere or in pico ampere range. Okay, it is very small. Now this photo generated current, that will be like, which was negligible in case of forward bias because the forward bias current is very high. In case of reverse bias, that small photo generated current will also be comparable or more, like much more compared to the reverse bias current. That is how we can actually detect the light. Okay, that electron hole pair is generated because of light, so there must be some light. That's how photodiode sense light. Okay, a certain wavelength. So that is why we use photodiodes in a reverse bias condition, not typically in forward bias. Okay, so this third statement is true. Last statement was the reverse bias current is sufficiently larger than the photogenerated current. So this is not true. We have already seen reverse bias. If reverse bias current is sufficiently larger, then we would not be able to detect the photogenerated current. Okay, so the photogenerated current must be higher compared to the reverse bias current, then only we can detect light using a photodiode. So the correct answer is B. Only the third statement is true, all other are incorrect, and I hope that you got the point why these are incorrect. So you have to go through all of the statements one by one. Okay, I hope it is clear. Is there any question? Because it's already 7:57. I had few more questions, but I will consider those in the next sessions. It's already time. If you have any question, you can ask. Otherwise, we can stop the session. We can end the session here. You will get the recording of the session. This will be available, like you can go to the course. I have not uploaded right now, so I'll upload, and then you can find the problem solving sessions. There will be below the class content, you will find there. Just go to the NPTEL page for sensors and actuators. Okay. Okay, if there is no question, then thank you everyone. Thanks for attending the session. I hope this was useful, and see you in the next weeks. I hope that you will come and learn in these live sessions. Okay, thank you.